So it says solve it. So solve the following exponential equations. Record the equations you are not sure how to solve. Okay, so obviously we see that these two bases are the same, which means that this exponent must be the same, right? So x equals 3. Over here, we've got 2 to the first power on this side, so x is going to equal 1. Okay? We've got 2 to the x right here equals 16. Well, this is a little bit trickier. What power do I need to raise 2 to get to 16? Well, 2 raised to the first power is 2. 2 raised to the second power is 4. 2 raised to the third power is 8. 2 raised to the fourth power is 16. So x is going to equal 4. Okay? Now here's where it starts to get a little bit trickier. We've got this equation right here. So we're going to move that 64 to the other side. So this should read 2 to the x equals 64. So we've got to figure out 2 to what power will give us 64. Now, we could actually do this using logs. Remember how we've got exponential and logs and they kind of go back and forth? I personally would start at my base, go to my outside, and then finish at my exponent. So I could write this like this, which is what we learned last week. Okay? So we're going to have log of 64 divided by log of 2. Log of 64 divided by log of 2. So if I put that into my calculator, what I'm going to get is, if I can use this mouse. Nope. Just kidding. Doesn't work. Okay, cool. So if I go into my graphing calculator and I type log of 64 divided by log of 2, then that's going to give me 6, right? So 2 to the 6th power is going to give me 64. Okay? Over here, again, we're going to move this to the other side. 2 to the x equals 1. Well, we know anything raised to the 0 power is 1. So x is going to equal 0. Again, this is where it gets a little tricky. We know that we've got 2 to the 3x on this side. And we know that 2 to the 6th power gives us 64. Notice how I can rewrite this 64 as 2 to the 6th power. So now our bases are the same. So I'm just going to take my exponents, set them equal to each other, and then solve. So x is going to equal 2. Okay, so again, I rewrote this as 2 to the 6th power. So my bases are the same. Then I can just look at my exponents. Okay, so over here, I'm going to repeat that same process. Except we know that 2 to the 5th power gives us 32. So now I'm going to just take what's in the exponent and then solve. So x is going to equal 4. Okay, so down here it says, how did the structure of these equations make them easier to solve? Well, all of these were in base 2, right, on the left-hand side. But then we took the right-hand side, and they were powers of 2, right? So we can raise 2 to the 3rd power, and we get a number, right? Okay, so why would this equation be more difficult to solve? 2 to the x equals 10. 2 to the x equals 10. Well, let's actually solve this out. If I put this in log form, I'm going to get log of base 2 of 10 equals x. And so I'm going to go in and I'm doing my change of base form that we talked about yesterday. And so I'm going to do log of 10 divided by log of 2. And that's going to give me 3.32. So that's going to give me a decimal, right? And that's not just like an easy whole number, right? So this would be a little bit more challenging because there's not a whole number to plug in here that's going to make this statement true. It's a little bit harder to solve. Okay, so we've got this bacteria population, and it says a bacteria colony starts with one bacterium, and we can see that at time 0 we would have 1, right? The population of the bacteria doubles every day. Okay, see how it's multiplied by 2 each time that we're going up, right? And assume that there's a 24-hour reproduction time. The function P of t equals 2 to the t models the bacteria population P on day t. So our first question is, how many days will it take the bacteria population to reach 8? So we want the bacteria to reach 8. And then what about to reach 16? Okay, so the population is P. Okay, so we got 8 and we're trying to find 16. Okay, so how many days is that going to take us? Well, if we look over here at our table, it goes ahead and tells us. But let's say that we don't have the table. Let's actually like solve this out. So we're going to have 2 to the t equals 8. Now, if I don't know off the top of my head what 2 raised to what power to give me 8 is, then I can use that log to help me solve. So this will be log of base 2 of 8 gives me t, which really is just log of 8 divided by log of 2. So I could go into my calculator and I could say log of 8 divided by log of 2. And that's going to give me 3. So come back in here. That gives me 3. And obviously we can see that's what our table told us as well. Okay. What about to reach 16? Well, again, I'd set that up the same way, except now I've got to have 16 right here. I'm going to have log of base 2 of 16. I'll do my change of base, and that'll give me 4. Now, it says how many days will it take for the bacteria population to reach 10? So we want to know when it's going to reach 10. Well, we don't see that in our chart right now. So let's actually set this one up. And again, we're going to use logs to help us solve. So we'll have log of base 2 of 10 to give us t. We'll go ahead and do our change of base form. And then we're going to go into our calculator and type that in. So log of 10 divided by log of 2, which is going to be 3.32. So come back over here. It's going to take us about 3.32 days. Okay, so a day and a third, or 3 days and a third of a day, right? Okay. All right, so we're going to solve the exponential functions, okay? So what's going to happen is you always want to have the same base on both sides. You can't solve it unless you have the same base. Okay, so we've got to go and say, all right, 32. We got to put it in terms of a base of 2. So if I don't know what 2 to what power will give me 32 is, I could just kind of break this down by dividing by 2 each time and see if it is a perfect power, if that makes sense. Okay, so for instance, if I divide it by 2, I'm going to get 16. If I divide that out, I'm going to get 8. And all the way down until I have no more 2's. So how many 2's do I have? 2, 1, 2, 3, 4, 5. So 2 to the 5th power is 32. So now my bases are the same. So I'm just going to ignore those and just look at my exponents. Okay. So it's pretty easy when it's just like a number equals 2 to some power, right? Now, on number 2, we have the same base. You always got to check the base, okay? And if they're the same, you're just going to drop the base. Yeah. And then you're going to take your exponent, set it equal to each other, and then solve like you would normally. So I would move all my numbers to one side. So I'm going to subtract 5 and move it over here. And so that's going to give me x minus 8 equals 2x. And then I'm going to subtract x from over here. And so x is going to equal negative 8. Okay, so on number 3, we see that the bases are all the same. That's great. Okay, but we do have to remember what our power rules mean. Okay, so if we are multiplying by the same base, we're going to add our exponents. Okay, and then we're going to set it equal to the other side. So it's kind of like your exponents create like a little equation for you. And then now we're just going to solve. So we can subtract 5 from both sides, and that'll give me 3x equals 2. We'll divide by 3 on both sides, so x will equal 2/3. And you can always go back and plug it in and check, because I'm a big fan of checking so I don't make mistakes. So I'm going to check this by taking 2/3 and plugging it into this equation. So we need to know what 2 to the 7th power is. That's 128. So I'm going to come down here. 2 to the 3 times, sorry, I need to use parentheses, 3 times 2/3 times 2 raised to the 5th power. And notice how they're both equal to 128, so I'm good to go. Alright, so it says loggerhead turtles reproduce every 2 to 4 years, laying approximately 120 eggs in a clutch. Using this information, we can derive an approximate equation to model the turtle population. As it's often the case in biological studies, we will count only the female turtles. We will start with a population of 1 female turtle in a protected area and assume that all turtles survive. We can roughly approximate the population of female turtles by that function. Use a table and a method approximating to find the number of years it's going to take the model to predict that there will be 300 female turtles. Give your answer to 2 decimal places. Okay, so really quick, before we move on, they gave us a lot of information that's really important. So they want us to leave it in 2 decimal places. Okay, so 2 decimal places after. And we're going to try to see when this equation equals 300. Okay? So it says, start by thinking between what 2 whole numbers would y need to be in order for 5 to the y power equals 300. Here's a table to get you started. Create as many tables as you need to approximate the years. Okay, so I'm going to come down here. And so let's just think about it. After year 1, I plug in 1 into this equation. I'm going to get 5 to the 1st power, which is 5. So there's going to be 5 female turtles after that. So I need like a bigger number. Let's do 5 to the 5th power. So 5 to the 5th power means I'm going to go into my calculator and I'm going to say 5 to the 5th power. Well, that's a little too big, right? That's 3,125. 3,125. Okay, so I know. Okay, so again, you can plug in a couple of numbers, and you can try to figure out which numbers it's going to be in between, right? But really, you could create that log function and use that change of base form to get you your answer. Okay.